Good day everyone! Today, we are discussing 32 phase shift keying or 32 PSK.
But first, we need to know what is phase shift keying. As shown on the slide, PSK is a digital modulation technique where we transmit data by altering the phase of a carrier wave. A key characteristic to remember here is that while the phase jumps to represent different beats, the amplitude and frequency remain constant. This makes the signal very efficient in terms of power and bandwidth. If we look at the waveform diagram below, you can see how this works in real time. The top signal is our binary input, and the bottom is the modulated carrier wave. Notice the points circled in red. These are the phase shifts. Unlike simple on-off signaling, we are changing where the sine wave begins its cycle. In a 32 PSK system, we have 32 possible starting points, allowing us to pack a significant amount of data into a single signal change.
32 phase shift keying or 32 PSK. This is an MRE encoding technique where our M value is 32, meaning there are 32 distinct symbols available. In this modulation scheme, we group incoming digital bits into sets of 5, known as pentabit. Each pentabit represents one of the 32 possible output phases. By using 32 different phases, we can transmit more data within the same amount of time compared to simpler PSK versions. A critical aspect of 32 PSK is how close these phases are to one another. To find the phase separation, we divide the full 360-degree circle by our 32 symbols. This gives us a very small separation of only 11.25 degrees between adjacent signals. Because these signals are so close together, 32 PSK is highly sensitive to noise. It requires a very high signal-to-noise ratio or SNR to prevent the receiver from confusing one phase for another. Because of this high susceptibility to bit errors, 32 PSK is less common in practical hardware than 32 QAM, though it remains a vital concept in theoretical communication design. Now, let's look at the efficiency of 32 PSK in terms of speed and bandwidth. The baud rate or symbol rate is significantly lower than the bit rate. Specifically, because we pack 5 bits into every symbol, the baud rate is exactly 1/5 of the input bit rate. This leads us to the minimum bandwidth requirement following the formula B is equal to F sub B over N. The minimum bandwidth required for 32 PSK is the input bit frequency divided by 5. This demonstrates the primary advantage of high-level modulation. We can transmit high-speed data using a much smaller slice of the frequency spectrum. So let's look at the logical mapping. Each 5-bit combination from 00000 to 11111 is assigned a specific phase. As you can see in this table, the phases increment by 11.25 degrees per step. For example, 00000 starts at 0 degrees or sometimes with an offset of 5.625 degrees depending on the design, while 00001 moves to 11.25 degrees, and so on, all the way up to 348.75 degrees. While we often use gray coding in practice to minimize bit errors between adjacent phases, the core logic remains this steady 11.25 degree progression. Now, we are exploring a 32 PSK modulation system implemented in MATLAB or Simulink. PSK is a digital modulation scheme that conveys data by changing the phase of a constant frequency carrier wave. Specifically, a 32 PSK allows us to transmit 5 bits per symbol, offering high spectral efficiency. Our simulation begins with a random integer generator. For the set size, we set it to 32 to match our MRA number. For the sample time, we set to 1 second per symbol. This block creates a random stream of integers ranging from 0 to 31, representing the digital data we want to transmit. The heart of the system is the MPSK modulator. MRA number 32. For the constellation ordering, we use gray mapping. This is crucial because it ensures that adjacent symbols in the phase circle differ by only 1 bit. significantly reducing the bit error rate or BER in noise environments. For the offset, notice the offset of pi over 8 or 0.3927 rad. This rotates the entire constellation, which can help in avoiding zero crossing or meeting specific hardware synchronization requirements. Here we see the resulting constellation. Each red X represents one of the possible 32 symbols. In phase is the horizontal axis, and quadrature or Q is the vertical axis. Because all points lie on a circle with a radius of 1, the envelope of the signal remains constant, which allows us to use more efficient or nonlinear power amplifiers. To prepare the signal for transmission, we use a square root raised cosine filter. 0.35 is our roll-off factor, so this determines the excess bandwidth. And we are using 16 samples per symbol. This filter performs two vital roles. Number 1, it limits the bandwidth of the signal to prevent interference with other channels. Number 2, it minimizes intersymbol interference or ISI. Finally, the complex baseband signal is split into its real or in phase and imaginary or quadrature components. The real part is multiplied by a cosine carrier, and the imaginary part is multiplied by a sine carrier. These are then summed to create the final modulated waveform seen in the scope. So we are using a carrier frequency of 10 Hz or 2 pi 10 rad per second for this simulation. In this slide, we examine the time domain result captured by our scope. This visualization is essential for understanding how abstract digital data is transformed into a physical signal ready for transmission. The data source or the top rays, this represents the random integer generator output. So each step in the staircase waveform corresponds to one symbol period or 1 second. And the vertical level represents an integer between 0 and 31, which are modulator maps to a specific phase on the circle. The carrier reference or middle trace, this is our sine wave carrier, oscillating at a constant frequency of 10 Hz. In a real-world system, this would be generated by a local oscillator, and it serves as the blank canvas that will be modulated to carry out data. And for our modulated output or the bottom trace, this is the final 32 PSK signal after undergoing pulse shaping and up conversion. Notice that at every 1 second interval, the waveform's phase shifts. These shifts are what actually represent our data. Unlike theoretical PSK, which has a perfectly flat top, you see slight rounding or variation in the wave's peak. This is the direct result of the square root raised cosine filter. By smoothing these transitions, we ensure the signal doesn't leak into adjacent frequency bands, making it much more efficient for real-world broadcasting.
Now, we will tackle about constellation. In digital communications, a constellation is a 2D polar plot used to represent the different signal states of a modulation scheme like PSK. It maps the amplitude and phase of the carrier wave onto a complex plane where the x-axis represents the in-phase component and the y-axis represents the quadrature component. A 32-phase shift-keying constellation has 32 distinct points arranged in a perfect circle around a center point. Each point is spaced exactly 11.25 apart, or 360 degrees divided by 32. All points lie on the same circle. The amplitude remains constant while only the phase changes. Now, we are going to derive the equations and find what are the 32 coordinates from input bits 0, 0, 0, 0 going to 1, 0, 0, 0, 0. Shown in the screen is the parameters and their value, where bits per symbol is equal to 5 bits, m is equal to 32, n is equal to 5, amplitude is equal to 1, and the coordinate mapping where I is equal to a cosine phase angle and q is equal to a sine its phase angle. Now, let's look at a technical visualization where we plot the constellation of 32 PSK using MATLAB. We plotted this constellation diagram using MATLAB to show exactly how the 32 states are organized. Because we have 32 distinct phases, we can calculate that each symbol or dot on the circle represents exactly 5 bits of data, since 2 raised to 5 is equal to 32. Mathematically, each point is separated by an angle of 11.25 degrees. Thank you everyone for listening and lending us your time. We hope that you learned something from us. Goodbye!